we'll do a quick recap of what we are going to need to know for the exam. You can have a cheat sheet just like for the first one, and it can be only one side of a sheet of paper, 8.5 by 11. Whatever you want to put on it is fair game. You will be given the equation sheet that is on the exam to practice. And I'm going to go ahead and just recap the chapters. They will be roughly equally weighted as best I can. So 4, 5, and 7 are what exam 2 is over. And so that's Newton's laws, circular motion, and momentum and impulse. So they do kind of all go together and work okay as a themed exam. And I will do similar to the first one, where it's sort of a story and you're going through and answering questions about whatever's going on. But the questions, like with the first one, they shouldn't be to where you need to know the answer from one question to answer another. I may have had one like that at the tail end, but every other question should have been possible to answer independently. And it will be similar here. So anyway, we'll recap the chapters real fast. The first page of chapter 1 is just sort of setting up things about mass and force, so that information is not necessary to know. You do need to know how to find net forces, but we're going to see ourselves doing that about 1 billion times throughout these next 3 chapters. So the first page is sort of a write-off. And then for Newton's laws, you largely need to know them more for calculation purposes, because the concepts are, there's really only one question I can ask for, say, Newton's first law, which is, what is Newton's first law? And it's a pretty reasonable thing to write on a cheat sheet. So I'm essentially just asking, hey, for that thing I told you, put on your cheat sheet. What does it say on your cheat sheet? Can you read it? Good. Okay. So that's why I don't really emphasize them as much unless I'm talking about how they show up in problems. So first law, it's good to know and remind yourself what it says. And what it says is, if there's no net force, the thing does not accelerate. As far as calculation goes, that's useful because it's saying if something is at rest, or it's moving at constant velocity, or it says it's in equilibrium, or it says the net force on it is 0. There's many ways to state this, but if it says any of those things, you can automatically, when you get to that step in these second law type applications where you're saying net force equals mass times acceleration, any of those statements let you say acceleration is 0. That doesn't mean you can always say this is 0. Otherwise, why wouldn't we just always say equals 0? It's only when the thing is not accelerating. If it is speeding up, slowing down, or changing direction, we're not allowed to do that. We do have to say MA and either find A or use the given value of A to find something else. Okay, so that's how the first law is useful in problem solving. The second law is the one that gets the most mileage in the problem solving aspect, and in particular this form of it, where we've split it into 2 separate components. This is the thing you write at the end of every table you do. So that would be similar to what I'd be asking. So for the first chapter, things about how would you find the net force? What is the acceleration for a couple different different situations? It might be I have one where something's in equilibrium and one where it's not. So one where acceleration is equal to 0 and one where it is not equal to 0. But a lot of the problems I could ask for chapter 4 are things like this. The concept problems I can ask about are more about the third law and then properties of forces. So the third law is the hardest to get your head around. And it says that if thing A pushes on thing B pushes back on thing A, no matter what. That's all there is to it. If A pushes on B, B pushes back on A. And the even harder bit, the even less obvious piece, is that it pushes just as hard. Both forces are equal, always. That's the thing we saw where when you are being pulled downward by the Earth, You might be like, okay, I guess I could buy that I'm pulling upward on it because that gravitational attraction. But then you think, oh, but the force I'm pulling with is way weaker, right? No, the forces are the same. You pull on the Earth just as hard as it pulls on you. The effect of the forces is what's different. So the acceleration, what the second law says you should feel as a result of that force, it's going to be a huge number for you compared to the Earth because your mass is tiny compared to the astronomical mass of the Earth. Okay, so third law is about those equal force pairs. And in solving calculation-based problems, that's more useful because it lets you make sure you've finished out the list. You can look at everything that the object you are asked to analyze. You're looking at everything it interacts with. And you know you're done listing all forces if you've listed everything it interacts with, because the third law says those are the only things that should be pushing back on it. All right, so again, most of this page, as far as like memorize or write down or whatever, not critical other than the statement of the third law. So you remember equal sized forces. Okay, this page is the most important one in the chapter because it tells you how to solve any problem involving Newton's laws. Does that mean it's easy? No, it just means this is the process we use no matter what kind of problem we're trying to solve. So we'll come back to this when we're looking at specific examples, but this is the be all end all of what you do for these types of problems. I won't ask you about the universal law of gravitation, the very general way we can calculate gravitational forces. I'm just interested in the everyday one, that weight on Earth is your mass times 9.8. And again, that mostly shows up in these problem solving things. I give you the mass, and you just have to remember that the weight, the actual force of gravity, is 9.8 times whatever number I gave you. Tension. Ropes are the easiest one. The tension is along the rope and it just transfers from one end to the other. So if I'm pulling on one end of a rope, whatever force I'm pulling with, maybe 50 newtons or whatever, there's 50 newtons on the other end of the rope pulling on whatever's attached to it. So ropes are not tricky. We won't need anything about pulleys, but things like this question are the extent of what you need to know about tension, is that it is just along the rope, like is in the diagram here, and it does depend on what else is going on in the problem. Think about the fact that you can pull on a rope harder and harder and harder and harder until eventually it snaps. That means tension can take on lots of different values, from 0 when you're not pulling at all to when you're pulling as hard as possible. That's the most tension you can get out of that rope. So it's sort of constrained by the other forces present, for instance, the weight of the engine. And that's why we had to solve for T1 and T2 here. Normal force. The main property that always gets messed up about it is it can very much for sure be a different number than the weight of the object. It can be less than an object's weight, it can be more. It is often equal for things on flat, level ground. That's redundant. Things on flat ground, and for things that are not feeling a lot of additional forces. So, for instance, this block, it is on flat ground, so that might sound like the normal force is going to be equal to the weight, but it's not, because you've got this additional force acting. And the normal force, like tension, is something that's just kind of whatever it needs to be in order for all of the things to add up to 0 or to mass times whatever acceleration is going on. So it is, again, sort of determined by the other forces present. I could ask an elevator type problem, but it is short enough, straightforward enough that hopefully you will feel okay about that kind of problem. I definitely ask about stuff on ramps because it is involved, but it is a procedure that you can follow, and you will be able to answer questions about something on a ramp just as well as you could something on flat ground. The main thing that gets missed here, though, is these angles. If the ramp is at an angle theta, whatever that may be, the angle between the weight vector and that normal or perpendicular direction, the direction the normal force is pointing there, that angle is also theta automatically. You don't have to go through this trig and geometry stuff we did every time. You can just know that whenever the ramp is at theta, this angle between the weight vector and the y-axis, y does not mean vertical, again, it means this perpendicular direction for things on ramps. That is the same angle as the ramp angle. For friction, the conceptual thing about friction mainly is that static friction is stronger than kinetic friction. And it may help to just start calling kinetic friction sliding friction. That's really the only difference between the two as far as what they're describing. Static is for stuff that's sitting still. Sliding is for stuff that's sliding. We just don't use sliding to describe it because then we'd have FS for both of them and it would get even more confusing notationally. All right, so the other thing is that static friction, it's not a fixed number. So kinetic friction, we can always use this expression right here. That's always at least approximately true. For static friction, you can use a similar expression if it's maximum static friction, the most you're going to get. But if we don't need that much friction in order for something to stay on a hill or not slide off from being pulled by something or whatever else, this is what we lean towards. And it's just saying that the friction is, again, whatever it needs to be to offset what's pulling on it. So an example I was looking at with someone today that can help illustrate this is, you imagine it could be a book being pressed up against a wall, but also this is how fridge magnets work, is they're being pulled in towards a wall by, in this case, it would be a magnetic force, or you could think of someone pressing with their hand a book against a wall. In doing so, that's a large normal force, and that can amount to a large frictional force. Okay, so you can get a large static frictional force, and the static friction is what keeps the magnet from sliding down the fridge, or it's what keeps the book from sliding down out of your hand. But that doesn't mean that the static friction has to be a huge value at all times, like the most possible. It just has to be enough to offset the book's weight. So say we calculate that maximum static friction is something like 10 newtons. Well, if the book only weighs 5 newtons, then static friction at that time, or for that book, the amount of static friction you need to hold it up is also only 5 newtons. If the book's a little heavier, 7 newtons, static friction is 7 newtons. If the book is 10 newtons, static friction is 10 newtons. If the book is 11 newtons, though, that's more than what static friction can do. It's not capable of it. And at that point, that's when the book's going to start sliding. And then the value of that frictional force will drop off, and it will drop off to some new fixed value. So it'll maybe drop off to 6 newtons, and that definitely cannot stop that 11 newton book from sliding. This is graphing what I just described. That static friction increases up till that maximum, the best it can do, maximum static friction, and then suddenly drops off to a fixed value. Okay, so you can only use this equation if I say something is about to slip, on the verge of slipping. You ask for like the fastest something can go before it slips, things like that. And again, you don't need to know the fine details of things like walking. Those are just to help understand how you work with friction. These last examples are very good ones to look back at, but especially before the kinematics part. I've already tested you on kinematics, I don't like to double down like that and do a lot of like, here's what's from last exam too. So I won't have kinematics on there. It will just be the force piece of this, not the kinematics part at the end. All right, for circular motion, the hardest part in this chapter that gets mixed up the most is direction of things. Velocity is just the direction that thing is going at whatever moment you care to look. So at this moment, the plane is going off that way. At a slightly different time, the plane is elsewhere along the circle and it's going off a different way, and so on and so forth. And you can remember or know which way it's going at any time if you imagine the string snapping at that instant. Which way is the plane going to go when the string snaps? Whichever way it was going at that instant, whichever way it's facing at that instant. So that's velocity. Acceleration and the net force on something in a circle, it always points towards the center. This is at the level of like acceleration is always 9.8 in free fall. It's a fact. And if you just always get mixed up on that, just write that down. For circular motion, acceleration is towards the center, velocity is tangent to the circle, meaning along it. Okay? And that's pretty much the direction rules. To work with centripetal acceleration, though, you sort of add it as an extra layer to your free body diagram analysis of things. It's a new thing in your toolkit to know that if something's moving in a circle, instead of your options for acceleration being either 0 or just some number, now you can say, well, specifically for circular motion, it's v squared over r along with whatever direction that acceleration is in. So in this particular problem, for instance, the acceleration at the moment we're looking at the plane, it is to the left if we're looking from the back of the plane, right? This rear view of the plane. And that's because to the left is at that moment pointing towards the center of the circle. That's why we use that negative right there. If you miss that negative, things can go wrong because sometimes you end up taking square roots with these kind of problems, then you'll have a square root of a negative and the calculator will not be happy with it. So remember that you need to account for the direction of the acceleration. But that's the only kind of new thing going on compared to chapter 4 as far as the analysis of these situations. Application stuff and then the tangents I like to go on are not relevant. So I'll go ahead and just cross that one out too. Satellites, the main thing for them is just this. Finding the speed of a satellite in orbit. And you actually have two ways. It is useful to know both. So there's the way that works for any circular motion. That's the one on the left. It actually doesn't have to be a satellite for that to be true. But this thing is only true specifically for satellites in orbit. And also just remember, satellite can mean anything orbiting something due to gravity. So it could be a satellite around Earth. It could be Earth around the sun. It could be a moon around Mars. It could be lots of things like that. Satellite does not mean a big metal thing. You won't have to do this more complicated version, at least directly. So to calculate the period, this right here, what's always or almost always easier is to find the speed first using this equation, and then combine that with this equation over here to solve for the period. This version just does all of that at once for you, but it kind of, in some ways, makes putting it in your calculator harder. So I would just do them one by one. All right, so this one is particularly good for circular motion. This one, not so much as far as like calculating that specifically, but this one is good. It's more like what I'd be asking. Banked curves won't be on there because this is all you got for those. There isn't really anything else I can say about them. And that again just means hopefully you got it on your cheat sheet, but I don't like questions like that. All right, momentum and impulse. So this is just a different way of looking at motion. Instead of forces and mass, you look at these new quantities, momentum and impulse. They are related to force and mass, though. Impulse is a force over time. Momentum is a mass with velocity. Impulse is what changes the momentum of something. We call that the impulse momentum theorem. And that's going to work even if the force is very complicated, because we can replace it with its average value. And that's the version we use for calculations. The impulse momentum theorem says the impulse, meaning the effect of a force over time on an object, determines how that object's momentum changes, meaning it was this value before, it's this value after because of that impulse. Right? And a problem like this, very much a good one to look at. Applications, no. Conservation of momentum, I'll just jump to this simplified version of it, what we ended up with at the end of quite a bit of reasoning. So this is the only thing, the only equation you need to calculate anything involving conservation of momentum, with one extra condition that can happen for completely inelastic collisions, which is that the final speeds are the same. It's easy to forget that. If something's stuck to something else, they got to be moving at the same speed. And that is what helps you kind of finish out problems that seem like you're stuck. For the concept piece of this, I'm really asking about when is momentum conserved for something and when is it not? And the answer is, if there's anything outside of the system you're considering that is exerting a force on that system, meaning pushing or pulling on things within that system, momentum is not conserved. So that includes friction, because typically, if we're including like, man and woman pushing on each other, if that's our system, friction is coming from the ice, which is not inside the system. If we are talking about just the man as our system, though, then even the woman pushing on him, this force of her pushing on his hand, becomes an external force and becomes a reason his momentum is not conserved. So you just have to think, is there something outside the box that is pushing on the thing inside the box? If so, momentum is going to change in some way. But for most of the problems, we assume there is nothing like that, and that's why you just keep applying conservation of momentum over and over and over. The steps to do it I give here. So you write down that equation every time, see if you can throw out anything to make the algebra easier, and solve. They're very just cut and paste, cut and dry. The other conceptual piece, the last conceptual piece, is how you distinguish different types of collisions. It's not that momentum is conserved in some and not in the others. It's conserved in all of them, again, if we say friction's not really having any major effect. In that large synthesis problem I had posted, I talk about what effect does it have and why you can ignore it. And that's not a crazy thing to assume. It's not saying the world has no friction. It's just saying it doesn't matter over a tenth of a second. Anyway, so the conceptual piece here is the distinction between elastic and inelastic collisions, and what determines that is not momentum, but kinetic energy, which now we have more of an idea what that is. But elastic collisions conserve kinetic energy. It's the same before and after. Inelastic, they don't. Every actual real-world collision is inelastic, but some get pretty close to elastic, and they are easier to solve and do math with. So you use that as sort of a branching off point to talk about more complicated collisions. This question right here is an example of a completely inelastic collision, where you had to do that thing I mentioned of saying V1 final and V2 final are equal. So I did that right here. And otherwise, it's still the same process as any other momentum conservation problem. All right, and this last page I had said in class already is not relevant for the exam. Do you have any questions?
I think the only thing that I wanted to like probably go over would be like the when we do the diagrams.
Mm-hmm.
I think that was it for me.
Okay, so just like going through how you set up the diagrams.
Yeah, like how would you? Because when I was doing like the homework and things like that, I kind of got me confused, like how to set it up.
Okay, so I'm going to just make up a problem and just show how I would start to analyze it. So let me come over to a blank page here. I maybe won't go through the entire thing because the algebra just is what it is, and most of the points in how I grade these is more in the upper part of the problem, meaning did you get to all of the steps before the part where you have to do a lot of algebra. So I'll pick one that is a little bit more complicated. So let's say we've got something on a ramp. I think there's a problem in the review packet like this, like a log being pulled up a ramp. But it just has a lot of different ingredients going on, so it's a good one to look at to see this process in full detail. And the question might be, okay, I know the mass of the log that's given, it's, I don't know, 100 kilograms. I'm given the maybe coefficient of friction between that wood of the log and then the surface of the ramp. Maybe it's 0.3. And, or actually, you know what? I could talk about if I give both, then what do you do? So maybe kinetic is 0.2. And that should be almost everything I need. Let's say the last thing is that the log is being pulled up the ramp at constant velocity. Okay, you may not believe it, but that's going to be enough to solve for, in this case, maybe let's say the tension in the rope. So he is pulling on one end, this little dude, but that pull is transferring to the other end because it's a rope. It just transfers to the other end. And then we look at some other forces. So I'm trying to analyze this to find tension, and it's acting on the log. So I should probably analyze the log. How do I do that? Well, what is the log interacting with? One thing I've already accounted for is the rope. I might look at that and say, well, there's also a little guy there. Are they interacting? No, they're not touching in any way. So the log doesn't care that there's a guy there. It only cares about the forces on it from things it is in contact with or at least interacting with. And that is going to be things like the surface of the ramp. There's technically two pieces to that interaction, but we like to split them up into those separate things. So there is the piece about the ramp is not letting the log fall through it, right? It's supporting the log, and that's the normal force. It should be perpendicular to the ramp. I'm trying to make that a little more perpendicular. All right, there's this other piece that's making it harder for the log to slide up the ramp, and that's going to be friction. What kind? Well, in this problem, the log is sliding up the ramp at constant velocity. So I'm in the realm of kinetic or sliding friction. That's a pretty easy one, but it might not even tell me exactly what's happening, and you have to determine it. In that case, you would need to know a little bit more. Maybe you were given the tension, but it's that comparison we talked about of how does that thing that's trying to make the log move compare to the thing that's preventing it. If it's less than the maximum static friction, then the friction is just whatever the pull is, whatever the tension is. If it's at maximum, they're still equal, but that's like the best case or the most friction you're going to get, and then it suddenly drops off. So anyway, that's just how you know for certain that this is kinetic or sliding friction. And then the last thing is that the log is interacting with the Earth as a whole, and this is through that gravitational force, or the weight, and we know that's just mass times g. Okay, so My first step really is to not try and make it too abstract. Just look at what's going on in this situation and imagine what's pushing and pulling on the log. But then it becomes more abstract when I need to solve the problem because it lets me get rid of anything that's not relevant to the problem. So here's my log now. It's a dot. Here's all the forces on it. And I have to ask myself, how do those combine together to sort of determine the behavior of the log? And so I'm going to need to find the net force, even without really worrying how that's going to get me to, in this question, I think I was saying I'll find the tension in the rope. I'm not going to worry about what I'm trying to find. Just I know how I'll get there is it's the same way I get there for any kind of question that could be asked. You follow through by making your free body diagram, finding components, applying the second law, and then solving for whatever's left. So let's kind of set that up. To finish out finding components, I actually need axes, and that's where we use the tilted ones for ramps. And in particular, if the ramp has an angle of, okay, this is the one thing I forgot. Let's say it has an angle of 10 degrees. This is also 10 degrees, the angle between the weight vector and that y-axis. All right, now I find my components. And this is really not a new step. This is how we do vector addition. It actually doesn't matter that there's forces that we're talking about. This is true whatever kind of vectors we'd have to add. They just happen to be forces. So I'll list them out. Tension, normal force, kinetic friction, and weight. And those are going to add together to give a net force. Tension is along the x-axis, so it has a positive x component. It has no y component to it. It's pointing purely along the x, so all of it is along the x. I don't need a sine or cosine here. All right, normal force is similar, but all of it is along the y-axis. None of it is along the x. The kinetic friction is along the negative x-axis. It's pointing down the ramp. So it has a negative x component. It also does not point in the y direction at all, though. So negative Fk. No sine or cosine needed. But now we come to the weight vector. It points along the negative x and negative y axes. How do I know? We'll look at that vector. It's sort of pointing down this way and down this way. I'm only allowed to draw components that are parallel to those axes, the x and y axes, because that's what components are, how much of the vector is along each axis. So the thing that can happen here is you just draw any triangle you can think of, and then you have no idea how to find the components, because that's not how you draw components. You need to think about only lines parallel to the axes are allowed. Okay, so this is the y component. It's going to be in the negative y direction. It is adjacent to the 10-degree angle. For adjacent, we use cosine. So that's what goes in this slot. For the other component, it's in the negative x direction, wx. Whoops, sorry. I sort of double counted there. Wx itself, the x component of the weight, is negative. It's equal to the weight times sine of 10 degrees, because this side is opposite the 10-degree angle. All right, we add down the list. And this will give me my components for my net force. T minus Fk minus W, Fn minus W cosine 10. So this whole thing is the overall force on the log in the x direction, meaning along the ramp. This is the overall force in the y direction, so perpendicular to the ramp. Newton's second law says I can always set those equal to mass times x acceleration, and then similar for the y direction. And right about here is where I start to think about the specific problem rather than the general procedure that I use to do any forces problem. Because I have equations now, but I need to start thinking about this situation. In this situation, the acceleration is going to be 0 for both directions because we said, and in the full problem statement, it would have said constant velocity. So that means it is not speeding up, slowing down, or changing direction. It is not accelerating. So that is a decision I have to make and some thought I have to put into that. But from there, I'm really just left with two equations and some unknown things. And so for the most part, it's algebra now. Like there's no physics left almost. The only physics that is really left is that weight is mass times g, and that kinetic friction is the coefficient of friction times the normal force. And again, mass times g for weight. So that comes from physical observations, but once you put all of that in, these are equations. You solve equations for something. And that also means that everything that comes after that right there, whatever horrible, gruesome algebra there is to come, it's like 1 point out of 12 or 14 for this question. Um, the correct final answer for, I guess it was the tension in this problem, 1 point. So if you can get to here, that's 12 out of 14. That's pretty darn good. Okay. Maybe it would be 12 points instead. I don't know. But anyway, this is a very involved problem. It has quite a few points to it, but the majority of them are to the parts that you do almost the same way, no matter what kind of problem you're dealing with. I had some questions over email about, I think it's conservation of momentum stuff. They asked about specific questions in the review packet. So let me get to 48 through 56. All right, so this is the impulse momentum stuff and then conservation of momentum. So all of these questions, or at least most of them, what I want you to notice is what's at the very beginning of each one of them. It's so similar that when I'm doing these kinds of problems where things are crashing into each other or pushing apart from each other, I just start writing that. Like it's unconscious at this point because that just is what you do for collisions. It's conservation of momentum. And I'm not saying that's obvious. I'm just saying if you see enough problems like this, you just start to realize it's the same damn thing, like in a good way, that you can start from there and you are likely to get to the answer. Now, if you see, instead of being asked about speeds, which is typically what's going on here, so what is the velocity of something? Right? Almost always speeds or velocities, stuff like that. The thing that is a little bit different is when they ask about force. And it's because forces don't show up in conservation of momentum because we sort of sidestepped around having to think about them by introducing the concept of momentum. But we can still calculate the force by using the impulse momentum theorem, this right here. Or even if you forget that, if you just remember, actually, that's just Newton's second law. So let me just show that as a reminder. We got this expression from Newton's second law. And so if I divide both sides by that delta t, I'll factor out mass, v final minus initial over delta t. Well, that's acceleration. This is just F equals ma. It's just the added step of you can use the average acceleration if you're only concerned about the average force, and that's all that is really necessary to consider when we're talking about impulse and momentum conservation and these kind of newer concepts. But now let me look at a specific problem and say how I would read through it to address whatever question is being asked. And you can see I'm labeling masses. I'm saying, all right, what is the speed initially of both things? Since she's standing, it's got to be 0. So it won't ever, or very often, it won't tell you outright the velocity is 0 in those words. It will say rest or stationary or something is hanging or the words that imply rest. But from those, you can still say velocity is 0 at some moment. And then you're relating that to what's going on later. So you're relating before something happens to after something happens. In this case, it's her kicking a rock. So the question is, if her velocity before, and so was the rocks, if they were both 0, and her mass is this, and the rock's mass is that, how fast are they both moving after the fact? Well, they tell us hers, but they don't tell us the stones, and so we have to solve for that. That's the one we're looking for. So these problems really, I think, just come down to identifying what goes where in the equation. And for that, you just have to be strict about identifying what is object 1 and what is object 2. The choice is up to you. There's no reason one thing should be called 1 or 2. You just pick, and you just stick with that. In this case, I picked that the woman is object 1, the rock is object 2, but then I just had to not mix myself up. This is me stating to myself, object 1, the woman, has an initial, so that's what the 0 means, an initial velocity of 0, nothing. And then I do the same for the stone. And then over here, I called it V2F because it's the stone that is being asked about. And I called that object 2 in the first place. And this is the velocity of the stone after the thing happened, after the event, in this case, the kicking. So it's V2 final. And if you're just very meticulous with your labeling, that's about the main thing that typically goes wrong in conservation of momentum problems, is you just put something in the wrong slot in these equations. You put mass of rock 2 in for mass 1 when you had decided originally that mass 1 was the woman's mass. Stuff like that. So that kind of addresses all the questions at once, 48 through 56, because it's the same procedure for every single one of them. And even more so than like Newton's laws stuff. These are very much start to end. It's the same type of problem. Any other questions?
I don't.
Okay. Well, I'm just checking my email real quick. I don't see any others. So that is going to be it for the review. But if questions come up tomorrow or over the weekend, just shoot me an email. Or if I'm in tomorrow, come by for office hours. And I will see y'all on Tuesday. We will keep going with Chapter 6, and then we'll have our exam on the following Thursday.